So this is Reigate College Maths Year 2 Statistics, and the second video on the normal distribution. This is on the standard or standardized normal distribution. We've seen the normal distribution. We've seen that it's a symmetrical, gives a symmetrical curve with the mean in the middle. But it's convenient often to transform any normal distribution into what's called a standardized normal distribution. So the standardized normal distribution, normal distribution has mean equal to 0 and standard deviation equal to 1. So we write it, and we usually use the variable z. Z is normal with mean 0 and standard deviation 1. So we write that 1 squared there. Obviously 1 squared is 1, so the variance, the standard deviation squared, is also 1. Now the way, and one more thing, we also use the symbol phi like this. That's a capital Phi. Phi of A is used to mean the probability that this variable z is less than A. So where we've previously written probability of x is less than a value, here we might write probability of z is less than a value, so this might be probability that z is less than 0.9, say, or probability that z is less than minus 0.2. We could also write the same thing here, phi of minus 0.2. The way we standardize normal distributions is via coding. So you'll hopefully remember coding from year 1. So coding, if we change our variable x into the standardized normal distribution z, we do that like this. So we say that z is equal to x minus mu divided by sigma. So the x minus mu, it means that every element of our distribution, we're subtracting the mean from it. So that means that we're now going to end up with, for x, we're going to have a mean of 0, and then we're also stretching it by dividing everything by sigma. So that means instead of a standard deviation for x of sigma, we're going to have a standard deviation for z of sigma divided by sigma, which is 1. So I think I just said that the standard deviation for x is 0. I meant the standard deviation for z is 0. So let's go and have a look at how we use this. Let's do some questions. So question 1, for the standardized normal distribution, find using your calculator. Well, some of these we don't need to use the calculator. We can just do this using what we know about the distribution of any normal distribution, not just the standardized normal distribution. So for question 1, A, the probability that z is less than 0. Remember that z has a mean of 0, so this is saying what's the probability that we're less than the mean. Well, that's just going to be equal to 0.5. For B, probability that z equals 0. Remember that for any normal distribution, because it's a continuous distribution, the probability that it's equal to a given value is going to be 0. So for C, the probability that z is less than 1.2. Now what we're going to do is we're going to go to using the calculator. So using the calculator, I've already put in that we've got a mean of 0 and a standard deviation of 1. We now want our upper limit here to be 1.2. So there's 1.2, and let me just show you that I've already put in a lower limit of minus 100. So if we just draw a quick picture of this before we find the probability, we've got this, we've got 0 there, we've got 1.2 there, and we're going to be expecting a value. So we've got the whole of that tail. We're going to be expecting a value which is going to be bigger than a half, but of course less than 1. Less than 1. The probability is less than 1. So if we press equals, and we get the value 0.8849. So this is equal to 0.8849 or 885 to 3 significant figures. Let's look at D, the probability that Z is between minus 1.2 and 1.2. Let's go back to the calculator, and we're going to go and change that lower limit to minus 1.2. Minus 1.2. So we're now going from minus 1.2 to 1.2, and we press enter, and there's our probability of 0.7698. So 0.770 to 3 significant figures. So probability that minus 1.2 less than Z less than 1.2 is equal to 0.770. E, probability that Z is greater than 1.2. Well, we've already found the probability that Z is less than 1.2, so the probability that Z is greater than 1.2 is just 1 minus that, which is 0.115. Or we could put it into the calculator with this time a lower limit of 1.2 and an upper limit of something large. F, the probability that Z is greater than 0.9 and less than or equal to Z is less than 1.4. This less than or equal to here makes no difference. Less than and less than or equal to in a continuous distribution are the same thing. So let's put those into the calculator. So let's go to minus 0.9 and this was 1.4. Enter, press equals, and we get 0.735 to 3 significant figures. 0.735 to 3 significant figures. So that's that first question 1. Let's look at question 2 now. Question 2 says the random variable x is has mean 5 and standard deviation 0.1. For each of the following values of x, write down the corresponding value of the standardized normal distribution z. So what we're doing here is we're using our z equals x minus mu divided by sigma. So z equals x minus mu over sigma. So for A, x equals 4. Sorry, we've also got x is 5, 0.1, squared. So mean equals 5, sigma equals 0.1. Just to be absolutely clear, I think it can be quite helpful to write those things down. So z equals, our value of x is 4, minus our value of mu is 5, divided by sigma 0.1. Oh, should put 5 in here. There we go. X minus mu divided by sigma. So that's minus 1 over 0.1, which is minus 10. For b, we're just going to use this formula again. X equals 6, z equals 6 minus 5 over 0.1, which is 10. And for c, oops, I'm far enough down, there we go, that's better. X is equal to 4.5, z equals 4.5 minus 5 over 0.1, 0.5 over 0.1, minus 0.5 over 0.1, which is minus 5. So then, just to be clear, if we wanted to find the probability that x is less than 4.5, say, it would be the same as finding the probability that z is less than minus 5. Okay, so let's go and look at question 3 now. So question 3, can't see it there. Let's get that on the screen. There we go. That's more sensible, is it? So we've got x is normal with mean 100 and standard deviation 10. So we need to write these probabilities in terms of phi of z. So for a, probability that x is less than 100. So we're going to turn it into a probability for z. So if I say that our little variable x equals 100, so z equals x minus mu over sigma, which is 100 minus, what's the mean of x is 100 over 10, well that's just 0, so this is equal to probability that z is less than 0, which is phi of 0. Now it might have been obvious to you straight away because this is the mean, but worth looking at the method as well. So the method will make more difference in the next two questions. So B, probability that x is less than 110. Again, we're going to turn our x into a z, so our value of 110, so 110 minus 100 over 10 is equal to 1. So this is probability that z is less than 1, which is the same thing as saying phi of 1. Oh, sorry, this was the probability that x is greater than 110. Let's just do this properly. So I misread it. X is greater than 110. Well, that's going to be equal to 1 minus the probability that x is less than 110, which is 1 minus phi of 1. Okay, let's just see if we can fit the last question in there on this page. So we are now going to find the probability that x is between 90 and 105. So C, you see that x greater than 90, less than 185. So again, we've got to convert these values of x from 90 and 105 into values of z. So that's going to be 90 minus 100 over 10, which is minus 1, and 105 minus 100 over 10, which is 0.5. So this is the probability that z is greater than minus 1, less than 0.5. We sketch a little graph of z now. Looks like this. We're going from 0.5 there, the mean is 0, minus 1 here, so we want this area in the middle. We get probabilities less than a value, so this is 5, 0.5 is this whole thing, 5 minus 1 is this, so this is equal to phi of 0.5 minus phi of minus 1. So that's it for this introduction to the standard normal distribution. We'll see that this is much more use really when we come to use the normal distribution in reverse and find out an unknown mean or standard deviation or both given probabilities and values of our distribution variable x.